good is it that it's Friday, even if it's rainy? I'm very happy. Get a couple days to catch up and restore. All right, so a reminder that we have an exam on Monday. It's going to cover the material through today. If you check your email, or if you've seen in the email or in the Brightspace announcements, I posted what the help sheet will look, or the reference sheet will look like, and as well as a study guide that has some sample questions. So after class today, I will post the last of the video recordings of lecture. I think I'm all caught up till today. I'll post the, thank you. I'll post the lecture notes with my annotations on them. And I will post answers to the questions on the study guide. So, anybody else need the handout? Okay. And so at the end of last class, I told you, try to do this one at home. And so I will also post the answer to this, but not just with the geometry, but also with how to figure out the hybridization, which is the topic for today, okay? So. All right, so just to kind of summarize, so here we are, we've drawn Lewis structures, and we've used that, yeah. Oh. Come on. Let's see if we can get these two. And if we flip it, projection does not want to cooperate in the rain. There we go. Yay. All right. Thanks for letting me know, because otherwise I would have just talked and talked and talked. Those who just came in, there's a handout up here. I'll just leave it on the desk. You can pop up and catch it. All right. So we draw our Lewis structure, and we figure out the number of structural pairs and the number of lone pairs. So the number of things, areas of electron density that surround your central atom. Okay, and from that we can figure out geometry. What directions in space the bonded atoms are pointing, so where are their nuclei positioned, okay? And so when we have those shapes, okay, then what we can do is look at the electronegativity of the atoms involved in bonds, figure out if a bond is polar or not, and which way the bond dipole points. And then we look at the distribution of bond dipoles, how they're arranged in space, and we can tell if our molecule is polar or not, okay? So just to kind of summarize this and to give you a sort of big picture of the trends that you see, okay, when your electron pair geometry is linear, okay, your molecule will be nonpolar if both groups are the same. Okay, so if, then your molecule will be nonpolar, okay? So if you have trigonal planar geometry, okay, and we looked at one of these examples, that was our three-way tug of war, if all the groups around your central atom are the same, okay, all three of those atoms are going to be pulling on the electrons with the same force, if you will, and so that will make a nonpolar molecule because all the dipoles are going to add up to 0. Okay, so when we go to sort of higher level geometries, if you have tetrahedral, it's all four things are the same. So hopefully you're seeing a pattern if you've got symmetry and you've got the same thing attached to your molecule. So again, whether you have 5 groups or 6 groups, if everything's the same, okay, then you're going to have a nonpolar molecule. Okay, so that's an easy way to spot something that's nonpolar. Okay. All right, so general rules, if we have lots of symmetry, okay, so that's, if you're looking at things from different angles, it looks the same, okay, that would be a symmetrical molecule. If we have symmetrical molecule and no lone pairs, that's going to be nonpolar, okay. Hydrocarbons, okay, hydrocarbons we haven't used this term extensively, but they're molecules that are made up just of carbon and hydrogen bonds, okay? So molecules with only carbon and hydrogen, okay? So we can have something that looks like this. All right, or we could have something where, we've got lots of hydrogens and no multiple bonds, but the point is, if those are the only 2 atoms you have in your molecule, the only 2 elements, that's a hydrocarbon. Hydrocarbons are nonpolar, okay? And so things like, vegetable oils or, the oil that you would use in your car is not a pure hydrocarbon. They have other groups, but the majority of the molecule is this big nonpolar hydrocarbon chain. Okay, and so nonpolar things we tend to think of as oily or greasy molecules or materials. Okay. All right, and then a quick way of spotting something that is polar, okay, is a molecule that has NH or OH bonds. Okay, so these are going to be bonds that are polarized towards the non-hydrogen atom, okay? So the bond dipoles will look like this. And we tend to have, and these tend to be found in groups that, these types of bonds tend to be found in groups that are kind of at the end, right? So let's think of a molecule that everybody at least has heard of. Okay, so this is ethanol. And does ethanol mix with water? So here's our polar bond here. All right, so here's an example. Ethanol. Does ethanol mix with water? Do beer, wine, and vodka exist, right? Those are all water-based solutions that happen to have alcohol in them. Water's a polar molecule, ethanol's a polar molecule, like dissolves like, they'll mix, okay? So this is a polar molecule. And again, it's got a nonpolar portion, right? This part has nonpolar bonds, and this part is nonpolar. But we've got this polarized portion. We've got some lone pairs here, okay? And that's enough, okay, to make your whole molecule polar, okay? So this is the polar part. So if we were to look at this, we would find that the molecule has a molecular dipole that is, that points kind of like this way, okay? This would be the molecular dipole. Okay. So it mixes well with water, what we would call a polar solvent. Okay, so solvent would be your liquid that is dissolving or mixing with your other polar substance, okay, in this case, the alcohol. All right, so what we're going to talk about for the rest of class today is we're going to look back at bonds and think about what orbitals are doing. okay? So we developed this notion of orbitals as the regions of space where you're likely to find electrons, okay? And then we figured out in atoms how electrons are arranged in orbitals, okay? Then we developed the concept of valence electrons and used those to draw Lewis structures that are telling us how, how atoms are bonded to one another and, whether there are any lone pair electrons or unpaired electrons in your molecule, and how we can use that to determine shape and polarity of the molecule. So now we're going to go back and look at how we resolve an inconsistency with our view of atomic orbitals, okay, and where electrons actually exist in molecules. Okay, so there's atomic orbitals, which are, where electrons are most likely to be found. In an atom, okay? But when you add other atoms, when you add more than one atom, right, you've got multiple nuclei, and that's going to be multiple influences on your electron and where it can be, okay? So molecular orbitals, okay, there's something called molecular orbital theory, which we're not going to go into, but we're going to talk about valence bond theory. Okay, so let me catch up to myself. So where electrons are most likely to be found in a multi-atom molecule. Right, so that's multi-atom just means you have more than one atom there, right? Okay. So, and it's not going to be the same, okay? So when you have one nuclei that's attracting your electron, okay, it's going to have, a probability of being in certain places given the amount of energy it has. You take that same electron, okay, and you involve it in a bond to another atom, another nucleus, okay? And there's going to be new forces acting on it, okay? There's here we have protons in one nucleus. Now when we have two atoms bonded together, we've got two nuclei, two regions of positive charge that are influencing where that electron's going to go. And so we need sort of a new model, a new level of theory to deal with electrons in molecules as opposed to electrons in single atoms, okay? And if we go through, quantum mechanics and you do all the mathematics involved with those equations, okay, we just need that one theory and we can deal with molecules or atoms, okay? But when we talk about things like VSEPR theory that we use to get those ideal geometries, that is in essence a simplification of the quantum mechanics, okay? So the valence bond theory that we're going to talk about, okay, is a way of thinking about where electrons are. It's going to be a simplification and an approximation, okay, that's not going to give us kind of an exact answer. It's going to enable us to predict a lot of things and a lot of properties, but there are things that it won't allow us to predict. Every time you simplify a theory, okay, there are areas where it's going to break down, okay? However, it can help us to understand and resolve some of the conflicts that, if you really wanted to sit down and think about, okay, my electrons are in my orbitals in my carbon atom, and it now bonds to a hydrogen atom, like, what's going on with those orbitals? Okay, so that's what we're going to talk about right now. Okay, so valence bond theory, okay, is a way of thinking about electrons in molecules, okay? And so we're not going to be using the concept of the atomic orbital. We're going to be using the concept of what we call hybrid orbitals, okay? So this is our new concept. All right. So what's our idea of what a chemical bond is? Okay, it's sharing electrons, okay, between two atoms. And how is that shared? Okay, we have orbitals that overlap between atoms that are next to one another in space. Okay, so that's what we mean. Okay. So we know that electrons repel each other, and so they're going to arrange themselves around your central atom in order to avoid each other, right? This is electron repulsion, or electron pair repulsion. That's the EPR of our VS-EPR theory, right? So we actually have two bonding theories, okay, and they're called valence bond theory. This is the one we're going to talk about. Okay. So another bond theory, the more sophisticated one, is called molecular orbital theory. And we don't have time to cover that, so we're going to just focus on valence bond theory because it gets us quite far. Okay. The differences between the two, okay, are going to be how the specific location of an electron involved in a bond is determined, how its energy is, and how we explain unpaired electrons. Okay, so we've got two bonding theories that differ really in specifics. Will be, and how to determine their energies. All right, so when would you want to use molecular orbital theory? Okay, so valence bond theory works well for lots of things, particularly organic molecules, okay, and that's why you can get through, general and organic chemistry with only thinking about valence bonding theory when you're trying to determine reactivity of carbon-based compounds, okay. Molecular orbital theory, again, is more complicated, but if you want to think about bonding in atoms that are beyond the p block, okay, so if we want to be thinking about some of our heavy metals, right, we need molecular orbital theory, okay, so needed for, let's say, elements. But again, if you're talking organic chemistry and you're dealing with, carbons, hydrogens, nitrogens, oxygens, things like that, valence bond theory works pretty well. All right, so what is valence bond theory? Okay, so first of all, any bonding theory, okay, is going to acknowledge the fact that the bonding electrons, okay, achieve a lower energy configuration when the bond is formed. And remember, one of our rules of the universe is molecular systems like to be at their lowest possible energy, okay? So, for any bond, okay, the valence electrons involved, and it doesn't matter which theory you're using, have a lower energy in bonded form, okay? And that's as opposed to just being in an isolated atom. Okay? So that's why bonds form, right? Because by doing this, and I can be at a lower energy. Okay? So what does valence bond theory add to this? Okay? Well, the first thing, okay, is it says that, again, our orbitals are going to overlap. So orbital overlap, key feature. Okay? Second thing, okay, is your valence electrons are either going to be between two atoms, okay, so they're going to be shared, or they're going to reside on a single atom, okay, and that's what we have, our lone pairs. So, okay, we've got our bonding pairs and our lone pairs. That's nothing new to us, okay? And valence bond theory defines two types of bonds, okay, a sigma bond and a pi bond, okay? So sigma bond, we use a lowercase Greek letter sigma for. Pi bonds, we use a lowercase Greek pi. All right, so let's talk about what sigma bonding is, okay? So the key feature, okay, the most important thing to remember about a sigma bond is that if you draw a line between the two nuclei of the bonded atoms, your sigma bond is the area of electron density that represents the bond is going to be directly on that line between the two atoms. We're going to call that the internuclear axis, okay? So a sigma bond, our key important thing is that the bonding electron density, our bond, okay, is along the axis between the two nuclei. So the first simplest way of visualizing this is I've got two hydrogen atoms, okay? And we know that hydrogen exists in the air we breathe as H2, right? And so when we have two hydrogen atoms that are going to form a bond, okay, each hydrogen atom has a single 1s orbital. All right, so our single 1s orbital is just a sphere surrounding the nuclei, and so if we move those atoms close enough, okay, they're going to have a region of overlap, okay? And this is where our bonding atoms, okay, would spend their time living, if you will, or residing. So now, if we want to talk about hydrogen with its 1s orbital, okay, bonding to an atom that has electrons in a p orbital, say, okay? Remember that we have p orbitals that go in three directions, right? Ones that lie right on the x-axis, ones that lie on the y-axis, and ones that lie along the z-axis, okay? So if I have a p orbital, okay, it can overlap with hydrogen's s orbital, okay? They can line up, okay, and then I can get a bond. Now let's think about two fluorine atoms, where the two fluorine atoms, okay, have electrons in a p orbital, okay? In order for there to be overlap, okay, those p orbitals have to be on the same axis, okay? They both have to be, well, so let's think about our fluorine atom, okay? It is, so we're going to have, it's going to be 2p6, right? So we would have our, let's see, our s electrons. This is for fluorine, okay? And we'd have 2 in the 2s. So that's 4. So we have to do 5 more electrons, right? And so we'd have 1, 2, 3, 4, 5, okay? So this is X, Y, and Z, okay? So if I have 2 fluorine atoms, okay, their available valence electron to be, the one that's available to be involved in bonding, okay, is going to be in the 2pz orbital for both of them, okay? So those orbitals are going to line up because they're pointing in the same direction in space, okay? And so the overlap would be in the region, again, between those 2p orbitals, okay? Now, so again, notice that we've got, you know, spaces where there's no overlap in all these scenarios, okay? So one of the things that I hope is kind of clear from just looking at these pictures is that the shapes of where the electrons are going to be in molecules is not going to be the same. They're going to be slightly different shapes, okay, than they are in isolated atoms, okay, because my electrons are going to be at their lowest energy state when they're in this region where there's orbital overlap, okay? So the likelihood of them being here or here is going to be lower, okay? Whoops. There we go. All right, so if we want to look at the methane molecule, okay? I'm just going to quickly do the carbon orbital diagram, okay? So carbon has how many electrons? How many valence, or how many electrons total does carbon have? 6. So 1, 2, 3, 4, 5, and 6, okay? All right, so, but carbon has how many valence electrons? 4, right? So we've got 4 valence electrons. 2 of them are paired, and 2 of them aren't, okay? So when we say that, you know, carbon is going to make 4 bonds, right? We're going to have overlap between an electron that's in a 1s orbital, okay, in the hydrogen atom. And then if we're going to have overlap between the carbon valence electrons and the hydrogen valence electron, some of those valence electrons are going to be in an s orbital, and some of them are going to be in a p orbital. Okay, so that overlap would look different if we kept the shapes that we have in the isolated atom. Okay? All right. So we can't just say, okay, so in this case, again, we've got some in an s orbital, some in p orbitals. Okay? So we can't just do this kind of picture where, okay, the p orbitals line up and they overlap, because for 2 positions, we would have, you know, something like this if we were doing the carbon and the hydrogen bond. But for 2 of them, we would have something like this, all right? But we know from experiments on molecules, okay, that those 4 hydrogens that are attached to that carbon arrange themselves in a symmetrical way, okay? So that simple geometry of, you know, of these orbitals overlapping as if they were in isolated atoms doesn't quite hold up, okay? So what we do, okay, is, so these are, again, what our orbitals look like for the central atom, right? So we've got something in a 2s, 2py, X and Z. All right. So the directions of the orbitals, okay, if we were just to look at where the orbitals are pointing, okay, they don't match the geometry that we know that methane has, okay? So this is so it's molecules like this, okay, that led to the development of new theories of where electrons are when bonds between atoms form, okay? So led to the development of valence bond theory and molecular orbital theory, because we can't just stick with, we've got atomic orbitals and they overlap, because if we were to put them in the places where they overlapped, the atoms would wind up not in the places that we know that they are when we do physical tests to determine the structure of molecules, okay? All right, so we have to have a new concept, okay? So we need a new idea of where the electrons go in bonds, okay? And so that's where valence bond theory comes in, okay? And the idea that, you know, just making these things, you know, overlap doesn't give us the right shape, okay? It makes some sense when you think about when you add another nuclei, okay, now there are different forces on the electron. So it makes sense that the electrons are not going to be in the same place, okay? All right, so the concept, the big idea that we introduce is that there are things called hybrid orbitals, okay? So the problem that we had, okay, is in molecules, the orbitals, the atomic orbitals, and the shape the shape of a molecule, okay, doesn't go in the same directions as the atomic orbitals, okay? So the solution that valence bond theory proposes is quite simple, okay? It's the concept is simple, okay? The implementation is a little bit more complicated, okay? And that's just, okay, so the atomic orbitals, where the electrons go, is just a different shape when it's in a molecule, okay? So we have new shapes, okay? And we call those new shapes hybrid orbitals. Okay? So in valence bond theory, we call them hybrid orbitals. In molecular orbital theory, we call them molecular orbitals. Okay, so we're going to be talking about hybrid orbitals. Okay? So, and you can think of this conceptually as the two orbitals, the regions where the electrons would be found in the individual atoms, combine in a new way to make a new shape, okay? So you can think about it if you've ever, you know, just looked at waves in the water, okay? And you throw like a rock in the water, right? And it makes some waves. And if you throw another rock in and it makes waves, when those waves kind of approach each other and come together, sometimes they cancel each other out, and sometimes they make a bigger wave. So this is one of the things that I absolutely despise about wave pools at water parks. They scare the living daylights out of me because I've seen too many kids come up with bloody noses. But when you start getting the wave pool, right, you know, it makes waves of a certain size, but then once it's been going for a while and people are splashing around in it, you can get bigger waves, right? And so the same thing happens when we're thinking about electrons as being these little wave-like things, okay? When you combine and mix these, okay, sometimes you're going to have bigger waves, which means, hey, the electrons are more likely to be here. And sometimes you're going to have them cancel out, and it's going to say, nope, the electron is not likely to be here. Okay, so that's where if we go back to this picture here, and we say, oh yeah, the electron's more likely to be here, and it's less likely to be here. Okay, that's how if we add these things up, it's how we're going to get those new shapes. Okay. All right, so the other key part of valence bond theory, okay, is that the hybrid orbitals go in the VSEPR electron geometry directions. Okay, convenient, right? Our observation is that our atomic orbitals aren't going in the directions that we know match the shape of the molecule. So we're just going to say the new orbitals go in the shape that we know the molecule adopts. And it makes physical sense, right, if we say that, because we have observed that that's the shape the molecule makes. All right, so the one key, okay, is that our hybrid orbitals have new shapes, but the same energy, okay? Okay, so, all right. So the way we're going to work at determining where hybrid orbitals, okay, and what they look like is, we go formula-Lewis structure, the structural pairs that help us figure out the geometry, that's going to help us figure out the hybrids. Okay, so if you look at, to skip to the punchline, if you look at the handout I gave you, okay, what you'll notice is it looks a lot like the table of electron or of geometries that I've given you before. Okay, it doesn't have lone pairs in it. It just has how many regions of electron density. So this includes bonding and lone pairs. It tells you what the geometry is. And then it shows you what we call the hybrid orbital, okay, and what shapes the hybrid orbitals take, okay. And the key way for me to remember hybridization, okay, is we have, is that the names of the hybrid orbitals, okay, and the numbers associated with them add up to the number of regions of electron density. So what do I mean by that? Okay, if you look, we have an sp orbital, okay, and I'm just gonna, let's see. Well, I'll get back to that. We'll just quick look at what hybrid orbitals look like, okay? So here's how they differ. Here are the orbitals in our atom. And again, we've got a sphere, and then we have them pointing in 3 different directions. And again, these directions are all 90 degrees from one another, but we know in tetrahedral geometry, we have 109.5 degrees, right? That's the shape. So the hybrid orbitals essentially look like the shape of our molecule, okay? And so what we do, okay, is we take, okay, the orbital types, okay, we've got s-type orbitals and p-type orbitals on our carbon, okay, and when they are in a molecule, okay, we call them sp3 hybrid orbitals, okay. Now, it's because they are a mixture of s orbitals and p orbitals, okay, that's where the sp comes from, okay, and we've got electrons, we've got 4 electrons, right? So we have to have 4 things, okay, in total where the electrons can go, okay? And so we're always only going to have one s-type thing in our hybrid orbital, okay? And we can have up to 3 p-type things, okay? So the number of things, okay, when we have s, p, and 3, okay, so that's 3 p-type things, 1 s-type thing mixing to form an orbital, or hybrid orbital, okay? And so if we count those, right, 1, 2, 3, 4. 3 plus 1 equals 4, okay? If we look then on our how many regions of electron density give us this, that sum matches the number of electron density regions, okay? Or otherwise known as structural pairs. And the nice thing about this is I can make this visible by changing it to white. So there we go, and moving this ever so slightly that way. All right, so that's what our hybrid orbitals look like. They're going to really look like these kind of pear-shaped lobes that go in the direction that our atoms, that our bonded atoms are going, okay? And so, you know, these would be the atomic orbitals for the carbon. This is what the hybrid orbitals look like, okay? And they match the directions of the structure, okay? All right. All right, so now we're going to talk about sigma and pi bonds. Okay, so sigma bonds are what we would think of as single bonds. Pi bonds are double bonds. Okay, so sigma bond is a single bond, and a pi bond is a double bond. Okay, so when we look at our methane molecule, okay, we have single bonds, and a single bond, again, is an sp3 hybrid orbital, again, between an atom with, you know, s electrons and one with s and p electrons. Okay. All right. So these are our types of hybrid orbitals. Okay. And when we're talking about hybrid orbitals and hybridization, we're only talking about sigma bonds. Okay. Because hybrid orbitals and sigma bonds, the key is that everything is on the axis between the two nuclei. Okay? So sigma bond is along the axis between the nuclei. So if you're asked to figure out the hybridization around a central atom, we're only going to think, we're going to treat it, we're just going to consider the sigma bonds, okay? Hybrid orbitals. Okay. All right, so this is just a chart again of all of the types of hybrid orbitals that we talk about and how they correspond to the geometry, okay? And again, you'll notice that the number of kind of things in our hybrid matches the number of structural pairs. So if we go down to our octahedral geometry, okay, when we say we have sp3d2, okay, this is one thing, this is three things, this is two things, that adds up to 6, okay? So we've got sp, sp2, sp3, sp3d, and sp3d2 for our 2, 3, 4, 5, and 6 things attached to your central atom, okay? All right, and so these are what the shapes look like, okay? And you'll notice that, again, all the hybrid orbitals look kind of like a fat lobe of a p orbital pointing in the direction of, you know, a bonded atom, okay? And I can't say this enough times, right? An orbital is just the area of space where your electrons are most likely to be. So this is the area of space where the electrons that are involved in that bond are likely to be. All right? So if we look, here's another sp3 bonding example with things other than carbon attached to hydrogens. And if we look, we've got the nitrogen atom here in ammonia. Okay, so this is ammonia. NH3. And this is methanol, CH3OH. Okay. So our central atom in both of these things that we're considering is going to be the carbon in one sense, the nitrogen in another, and we can also look about the oxygen. Okay. So if we look at the hybridization around ammonia, we've got 1, 2, 3, 4 things attached to our nitrogen. So 4 structural pairs. Okay. And that hybridization is sp3. Okay. So that's sp3 hybridization. Okay. And so it doesn't matter if it's bonding electrons or the lone pair electrons, okay? We have an sp3 orbital, and that's where the electrons are, okay? All right, so now let's look at methanol, okay? So this carbon has 4 structural pairs, right? It's got 4 bonds. So that is an sp3 carbon, okay? Now let's look at the oxygen. Okay. The oxygen has 2 bonds and 2 lone pairs. So that's 4 structural pairs. So the hybrid orbitals around that oxygen are also sp3. Okay. All right, so here's a non-sp3 example. Okay, so we've got around our boron, we've got 1, 2, 3 regions. So we've got 3 structural pairs. And so that gives us sp2 hybridization. Okay. All right. And this is just an example where we have 2 regions of electron density around our central atom. So this is sp hybridization. Okay. And again, these things are our sigma bonds. Okay? So, if you want to identify, okay, your hybridization from a Lewis structure, okay, what you're going to do is you're just going to treat regions of electron density as things. So let's look at one with multiple bonds. Okay, so let's just look at this, at our carbon here. So our carbon, how many things are around our carbon? How many structural pairs? When we have double bonds and we're talking about structure, we're just talking about regions of electron density. So whether it's single or double, it's just one thing. Okay, so that's going to be 3 things around it. So 3 things around it, our hybridization is going to be sp2. Okay, 1, 2, 3 things. Okay, so, and also, you just consider the sigma bonds, which are these things right here, 1, 2, 3. Okay? All right, so that's it for hybridization. So I will just look for this afternoon. There'll be an email that goes out that will tell you when, all the videos and the answers to the practice problems and everything are up. I will be, checking my email this weekend if people have questions or if you're having trouble with the homework, so let me know. And once again, I'll be here at least 20 minutes early on Monday if you want to come in and do the exam early, okay? Have a good one. Oops.